Differentiability talks about whether or not we can find a derivative. So we know that a derivative at a point is defined by this limit. The limit as x goes to a of f of x minus f at a all over x minus a. Or we can use the other limit. The limit as h goes to 0. Remember, h is that space between our x values. At f at a plus h, where a is our point where we're looking for the derivative, all over h. So these are two definitions of a derivative at a point. Remember, we're just looking at the little bit of the function right around the point. Now, if the limit doesn't exist, then there's no derivative there, because that's the whole definition. Remember, a limit doesn't exist when you have the right and left aren't the same, or when you just can't calculate it because it goes off into infinity or negative infinity or something like that. Now, what does our function look like for the derivative not to exist? Because remember, the derivative is the slope of the tangent line of the function. So for our function, for the derivative not to exist, you have to have a situation where you can't have a tangent line there. So for example, you could have a corner, like an absolute value function. Here, you're not going to have a tangent line at this point, because your tangent line is going to come along here, and then all of a sudden at this point it'll just shift over to this one. So the right and left limits when you try to take the derivative are going to be different. Or if you have what's called a cusp, which would be something like this. And again, the same thing, our tangent lines are going along, and then all of a sudden it's like you have to totally shift gears to get the tangent lines along here. So at this point here, we would not have a derivative because the tangent line coming from this side would be different from the one coming from this side. The other thing that can happen is if you have a vertical tangent line, because what's the definition of the derivative? It's the slope of the tangent line, right? And if you have a vertical line, what's the slope? It's undefined. So that means that you don't have a derivative there. Or you could have a discontinuity. For example, if you have a jump like this, then you're not going to have a derivative, because coming from this side you'll get one thing, and then coming from this side you'll get a different thing. The biggest thing that you need to realize for the derivative to exist is if you think about something being locally linear, then you'll be able to see whether or not you have a derivative. Because remember, in calculus we're looking at little bitty pieces of the graph. So what we want to look at is this is a tiny little piece of a graph. So for example, if we have, let's see if we can get this to work today. If we have, and it's gonna freak out. If we have a function, even a polynomial perhaps, like let's just say x squared. If we graph that, then we can look at this and you see the whole thing, but if we zoom in, let's just zoom in, let's go up a little bit off the origin and zoom in. And keep zooming in, and you see how when you zoom in around this point it looks like a line. As you're zooming in, if you look at it and it looks like a line, then you're going to have a derivative there, because you're going to be able to put a tangent line at that point that has a slope that's defined. So that's why we look at this term locally linear, so that we can decide if something is differentiable or not. We say that it's differentiable if it has a derivative. So let's look at another thing. If you have a differentiable function, so differentiability, then you know it's continuous. Because that local linearity, if you look at that, then it's a continuous function because it's all smooth and it's going to make sure that it's continuous. So differentiability implies continuity. So that means if you can find a derivative, you know that it's continuous there. But it doesn't necessarily work the other way around. Okay, not necessarily. Sometimes, but if I can spell necessarily. All right. So it doesn't necessarily can say if you have a continuous function, it's not necessarily differentiable, because like that absolute value function we looked at, it's continuous everywhere. But at this point right here, we can't find the derivative. So on page 108 in your book, you've got a really nice picture which can help us look at some ways to calculate these things. So you've got a function here, and you have this point, the x, where the x value is a, and if we go off a little bit, we've got a plus h, and we have a minus h. Now we were using for our definition of the derivative that's slope of the secant line, and then taking its limit as this h gets to 0, as the space between these parts. But sometimes that's harder to calculate. What happens if we have this line here, the secant line that's connecting these two between, the ones that are h on either side? Then we have the slope of it is the y value of the first one minus the y value of the second one, all over 2h. This is called the symmetric difference quotient. Now, why in the world is this even important? We know how to calculate a derivative, which is the slope of the tangent line here. The slope of this tangent line here is the limit as x goes to, let's do it with h. The limit as h goes to 0 of f at a plus h minus f at a all over h. So it takes this line here and moves the h till it's closer and closer to 0, so that we get this tangent line. And we know that this is the derivative. This is the derivative. That's how we calculate it. But this symmetric difference quotient, if you look here, you see that you can have a place where the secant line of this, where the slope is a symmetric difference quotient, is going to be parallel to the tangent line. So it can give you a good estimate. Now, why do we want to use that when we can just calculate it with a limit? Well, we don't typically use the symmetric difference quotient, but your calculator does. If you look on your calculator, if you go back to the home screen, first you have to get it to stop freaking out. So if you have a calculator here, graphing calculator, you can go to where it says math, and then you go down to number 8 where it says inderive, and hit enter. And what that's going to do is it's going to find your numerical derivative at a point, and it uses this symmetric difference quotient to do that. So it's using this formula here to calculate out your derivative. So what you have to do is you put the derivative. Remember, we talked about a little bit in class about these notations, and you looked in your book. This little d here and tells you it's taking the derivative of, and then the bottom is what variable we're taking the derivative with respect to, and then here's the function we're taking the derivative of, and then here we put the variable will go in for us automatically, and then we put the point that we're trying to find the derivative of. So for example, if we want to try to find the derivative with respect to x of x squared at the point x equals 2, then we can hit enter, and there it is. Now, if we have our function now, the way we would find the derivative, the f prime or the dx of x squared, is we would say the limit as h goes to 0 of, then we'd have, if we want it at x equals 2, then we would put it in at 2 plus h, and since we're putting it in the function, it would be squared minus 2 squared all over h, and we calculate that all out, and we get 4 plus 4h plus h squared minus 4 all over h. Taking the limit as h goes to 0, so those cancel, and then we can also cancel out an h, and we get 4 for our limit here, which is what they got on the calculator. Now you can also look at this symmetric difference quotient, and what it's doing in this is it's calculating this with a very small h, because it's actually, see here, we're not taking a limit. It's actually going to put in f at 2 plus, and then probably point, I think your calculator uses like 0.001 or something about there, and then f at 2 minus 0.001 all over 2 times 0.001, and let's see, we're running out of space here. Alright, so if we have that, we have 2 plus 0.001, and we square that, and we have 4.004001, and then we take f at 2 minus that, and we get 3.996001. So we subtract those, and we get 0.008 divided by 0.002, which is 4, which is what we got. Now in this simple illustration with x squared, whether we calculated out the actual derivative or we use the symmetric difference quotient like the calculator does, you get the same thing. You have to be a little bit careful with the numerical derivative on your calculator, because as the function gets more complicated, sometimes it'll be a little bit off, but most of the time it's pretty close here. So let's go back up and look at this. The biggest thing is you just have to realize that when you go to math and then down to where it says inderive, you're going to get this, and you'll be able to plug it in to do it in your calculator. Now, Here's the thing. Sometimes you're going to need to do that because calculating the derivative is by hand is just a long, horrible task, and it will take you forever. But most of the time, you will just need to do the derivative by hand. When we get started a little bit further into calculating derivatives, a little bit more simpler methods than writing it out with the limits, then you'll see that calculating the derivative of something like x squared should be about instantaneous in your mind. So putting it in the calculator will actually take you longer. But you need to know how to use this because there will be functions that are really complicated and we'll have to be able to use those. Now, there's one more thing in this section that we need to go over. Excuse me. We talked about the intermediate value theorem before. We talked about how if we had a continuous function, then we had to have those in-between values. And same thing is true with derivatives. If you have some x values, a and b, it would help if I could write properly, sorry, are any 2 points in an interval on which f is differentiable. Now that's important. It has to be differentiable on the whole interval. Then your derivative, f prime, takes on every value between the derivative at a and the derivative at b. What exactly does that mean? Well, it means if we have a function and we have this a and b here in this interval, okay, this is smooth and continuous and the limits are all going to exist, so it's differentiable and all of that. If we take our derivative, which remember is the slope of the tangent line here, at a, and then we take our derivative at b, then you notice that the tangent line turns as it goes up. In the middle here, it's kind of the slope is sort of between the two slopes of those. And let's see if I can get a different color here. So we have this in-between value, and the line just keeps tilting up. So what this is saying is on this interval, if it's all differentiable, then the slopes of the tangent line are going to just tilt up gradually and take all those values in between. So if we know we have a derivative of 3 at b, and we know we have a derivative of 1/2 at a, then everything between the 1/2 and 3 is every slope of the tangent line between 1/2 and 3 is going to have to be covered along this function between a and b. That's all the intermediate value theorem says. Make sure you kind of ponder that, think about that, and make sure you've got that. We'll go over some more of this stuff with finding the derivatives, deciding if it's differentiable, using the calculator to calculate the derivatives, and those kind of things in class. And make sure that we've got this section down. Make sure you've read the section. Obviously, I don't do the same examples as the book, so you need to make sure you've read it so you're getting the whole picture. And make sure that you've written down any questions that you have so that we can go over those in class.